Welcome, and a very peaceful evening to you. Tonight, we embark on the most detailed of journeys, a slow, contemplative walk through the entire history and scope of physics. We will not rush. We will linger on each idea, meet the people behind them, and explore the profound questions they sought to answer. Let the slow, steady rhythm of this story become the rhythm of your own breathing, guiding you into a deep and restful sleep. Our journey begins not with equations, but with a gaze towards the heavens. Long before it was a science, physics was a form of wonder. Ancient civilizations looked up at the night sky and saw patterns, but also mysteries. The planets, the wanderers, moved in loops against the backdrop of fixed stars. Why? The Greek philosopher Aristotle proposed a complex, Earth-centered universe, with celestial bodies embedded in perfect, crystalline spheres. This view held for nearly 2 millennia. The shift began quietly with the Polish cleric Nicolaus Copernicus. In 1543, on his deathbed, he published a book suggesting a simpler, more elegant model, a sun-centered universe. It was a radical, heretical idea that displaced humanity from the center of creation. The evidence for this new system came from the Italian polymath Galileo Galilei. In 1609, he pointed a new instrument, the telescope, towards the heavens, and what he saw shattered the Aristotelian perfections. The moon was not a smooth sphere, but covered in mountains and craters. Jupiter had its own moons, a miniature solar system that proved not everything orbited the Earth. Venus showed phases just like our moon, which could only be explained if it orbited the sun. Galileo was tried for heresy for these discoveries, but the truth could not be suppressed. He also made profound discoveries about motion on Earth. He rolled balls down inclined planes and demonstrated that all objects fall at the same acceleration regardless of mass, air resistance notwithstanding. He formulated the principle of inertia. An object in motion stays in motion. This was the crucial first step. The great synthesis was achieved by Isaac Newton. The story of the apple is likely apocryphal, but it symbolizes a profound insight. The force pulling the apple down is the same force that holds the moon in its orbit. In his monumental Principia Mathematica in 1687, he laid out his 3 laws of motion. The first law formalized inertia. The second law, F equals ma, gave us a quantitative tool to understand how forces change motion. The third law, action-reaction, revealed the inherent symmetry in nature. But his crowning achievement was the law of universal gravitation. He proposed that every particle of matter attracts every other particle with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This single mathematical law could explain the fall of an apple, the orbit of the moon, and the tides of the ocean. The universe, it seemed, was a vast, predictable, and beautiful clockwork. With the mechanics of solids and planets understood, physicists turned their attention to the phenomena we experience more directly: sound, light, and heat. Let us begin with sound, or acoustics. The ancient Greeks, like Pythagoras, understood the mathematics of music. But what was sound? Robert Boyle, in the 17th century, demonstrated that sound requires a medium by placing a watch in a jar and pumping out the air. The sound disappeared. Sound is a mechanical wave, a pressure wave. It is a series of compressions and rarefactions that travel through a medium like air or water. The Ernst Chladni, a German physicist, in the 18th century found a beautiful way to make sound visible. By spreading sand on a metal plate and drawing a bow along the edge, he made the sand arrange itself into intricate star-like patterns. These Chladni figures revealed the nodes and antinodes of the vibrating plate, a hidden geometry of resonance. Now, let us consider light. For centuries, philosophers debated its nature. Isaac Newton championed the corpuscular theory, that light was made of tiny particles. But others, like the Dutch scientist Christian Huygens, argued that light was a wave, pointing to phenomena like diffraction and interference. The debate would not be settled for another century. Meanwhile, the study of heat was also evolving. It was once thought to be a fluid called caloric that flowed from hot objects to cold ones. But the American-born scientist Benjamin Thompson, also known as Count Rumford, observed the immense heat generated by boring cannon barrels. He realized the heat was seemingly inexhaustible and was related to the mechanical work of boring. Heat was not a substance, but a form of energy. This was a crucial insight that would lead to a new branch of physics. The 19th century was the age of steam, and from the practical problems of the Industrial Revolution, a new, profound branch of physics was born. It began with the French engineer Sadi Carnot. In 1824, he asked a simple question: what is the maximum possible efficiency of a steam engine? He envisioned an ideal, reversible engine, now known as the Carnot cycle. His work introduced the concept that would become the second law of thermodynamics. Heat cannot spontaneously flow from a colder body to a hotter one. The formal laws of thermodynamics were then established. The zeroth law defines thermal equilibrium. If A equals B and B equals C, then A equals C. This is what allows thermometers to work. The first law is the principle of conservation of energy. It states that the total energy in an isolated system is constant. Energy can be transformed from heat to work or from kinetic to potential, but it cannot be created or destroyed. This united the concepts of heat and mechanical work. The second law, growing from Carnot's work, states that the total entropy, a measure of disorder of an isolated system, always increases over time. This is why a cup of coffee cools down, why perfume diffuses in a room, and why we remember the past but not the future. It gives a direction to time itself. The third law states that the entropy of a perfect crystal approaches zero as the temperature approaches absolute zero. It defines an unattainable absolute bottom to the temperature scale.
These laws govern everything from the efficiency of car engines to the fate of the entire universe, which is slowly and inevitably drifting towards a state of maximum entropy, a quiet and uniform heat death. While thermodynamics was being formulated, another even grander unification was taking place. For most of history, electricity and magnetism were seen as separate curiosities. The first connection was made by the Danish scientist Hans Christian Ørsted in 1820. During a lecture, he noticed that an electric current flowing through a wire caused a nearby compass needle to deflect. Electricity could create magnetism. This discovery inspired the English chemist Michael Faraday. With little formal mathematics but immense experimental ingenuity, Faraday discovered electromagnetic induction in 1831. He found that a changing magnetic field could induce an electric current in a wire. This is the fundamental principle behind the electric generator and the transformer, the technologies that would power the modern world. Faraday visualized these forces as filling space via lines of force or fields, a revolutionary concept at the time. The final, breathtaking synthesis was the work of the Scottish theoretical physicist James Clerk Maxwell. In the 1860s, he took the experimental laws of Faraday and others and expressed them in a set of just 4 elegant mathematical equations, Maxwell's equations. These equations described how electric charges produce electric fields, how currents and changing electric fields produce magnetic fields, and most astonishingly, how a changing electric field could produce a changing magnetic field, which in turn could produce a changing electric field, and so on, propagating through space as a wave. When Maxwell calculated the speed of these electromagnetic waves, he found it was exactly the known speed of light. He had proven conclusively that light is an electromagnetic wave. Furthermore, his theory predicted the existence of other types of electromagnetic waves, radio waves, microwaves, and X-rays, all invisible to the human eye, but obeying the same fundamental laws. The branch of optics was now fully absorbed into electromagnetism. It was one of the greatest unifications in the history of science. By the end of the 19th century, many physicists believed the major work was done. Lord Kelvin famously spoke of 2 small clouds on the horizon. These clouds would unleash storms that shattered the classical worldview. The first cloud was the constancy of the speed of light. The Michelson-Morley experiment failed to detect the luminiferous ether, the medium through which light waves were thought to travel. In 1905, a young patent clerk named Albert Einstein solved the problem with his special theory of relativity. He started from 2 postulates. The laws of physics are the same for all inertial observers, and the speed of light in a vacuum is constant for all observers. The consequences were revolutionary. Time dilation, a moving clock ticks slower. Length contraction, moving objects shorten. The famous equation E equals mc2 revealed that mass and energy are 2 forms of the same thing. In 1915, Einstein presented his general theory of relativity, which reimagined gravity not as a force, but as the curvature of space-time caused by mass and energy. Matter tells space-time how to curve, and curved space-time tells matter how to move. This theory predicted black holes, the bending of starlight, and the expanding universe. The second cloud was the ultraviolet catastrophe and the photoelectric effect. The German physicist Max Planck solved the first in 1900 by proposing that energy is quantized. It comes in discrete packets called quanta. Einstein used this idea to explain the photoelectric effect, suggesting that light itself consists of particles, later called photons. This wave-particle duality was baffling. The Danish physicist Niels Bohr applied this to the atom, proposing that electrons could only orbit at specific, quantized energy levels. But the full theory, quantum mechanics, was developed by a new generation. Erwin Schrödinger formulated a wave equation that described the probability of finding a particle. Werner Heisenberg introduced his uncertainty principle, stating that you cannot know both the exact position and momentum of a particle. At the subatomic level, reality is fundamentally probabilistic and fuzzy. Armed with quantum mechanics, physicists could probe the heart of the atom, leading to nuclear physics. Ernest Rutherford discovered the nucleus in his gold foil experiment. James Chadwick discovered the neutron. Lise Meitner and Otto Frisch explained nuclear fission, the process that powers nuclear reactors and atomic bombs. To probe deeper, we need particle physics. Using massive particle accelerators, physicists discovered that protons and neutrons are made of quarks. The Standard Model emerged, cataloging all known fundamental particles and 3 of the 4 fundamental forces. The Higgs boson, predicted by Peter Higgs, was discovered in 2012, confirming how particles acquire mass. We also have plasma physics, studying ionized gases that make up stars like our Sun. Geophysics applies physics to understand our planet's earthquakes and magnetic field. Biophysics uses physics to understand the mechanics of life itself, from DNA to the human brain. The journey of physics is endless. The mysteries of dark matter, dark energy, and the unification of gravity with quantum mechanics remain.
Welcome to our final journey together. Over these many stories, we have mapped the vast and intricate landscape of physics, exploring its separate territories, from the predictable paths of cannonballs to the ghostly dance of quantum particles. Tonight, we will not visit a new land. Instead, we will ascend to a vantage point from which we can see how all these territories connect, how they weave together into a single, breathtaking tapestry of understanding. This is the story of the unity of physics, a story of how humanity learned to read the cosmic code. So, find a deep comfort and let this unified vision lull you into a peaceful, contemplative sleep. Our story of unity begins not with complexity, but with a search for simplicity. For millennia, the heavens and the earth seemed governed by different rules. Then came Isaac Newton. With his 3 laws of motion and his law of universal gravitation, he achieved the first great unification. He showed that the force that makes an apple fall is the very same force that guides the moon in its orbit. The physics of the terrestrial and the celestial were one. This was classical mechanics, a powerful, deterministic framework that saw the universe as a magnificent, predictable clockwork. But this clockwork needed energy to run. This understanding emerged from the fires of the Industrial Revolution, giving us thermodynamics. The laws of thermodynamics, conservation of energy, and the inevitable rise of entropy governed the flow of this energy. They applied universally, from the steam in an engine to the nuclear fire in a star. They told us that the universe has a past and a future, an arrow of time inscribed in the very tendency of things to move from order to disorder. And what of the phenomena we couldn't touch? Sound was understood as a mechanical wave, a rhythmic compression of matter. Optics, however, remained a puzzle. Was light a particle, as Newton thought, or a wave? For a time, the classical world seemed neatly divided. Matter was made of particles, and light and sound were waves. It was an elegant but incomplete picture. The next great unification began with a seemingly simple observation. In 1820, Hans Christian Ørsted saw a compass needle twitch near a wire carrying an electric current. Electricity and magnetism, long thought separate, were intimately connected. The brilliant experimentalist Michael Faraday grasped the deeper meaning. He saw space not as empty, but filled with invisible lines of force, what we now call fields. A magnet creates a magnetic field in the space around it. An electric charge creates an electric field. Faraday visualized these fields as a kind of tension in the fabric of space itself. It was the theoretical genius James Clerk Maxwell who wove these insights into a mathematical tapestry of unparalleled beauty. His four equations, Maxwell's equations, unified electricity and magnetism into a single force, electromagnetism. And in a stunning leap, they revealed that light itself is a traveling wave of oscillating electric and magnetic fields, an electromagnetic wave. This was more than a unification. It was a revelation. The branch of optics was now a sub-branch of electromagnetism. The visible light we see is just one tiny window into a vast electromagnetic spectrum, from radio waves to gamma rays. The universe was speaking in a language of fields, and we were beginning to understand its grammar. Just as physics seemed complete, two revolutions shattered the classical picture, pointing toward a deeper, stranger unity. The first was relativity, born from the mind of Albert Einstein. Special relativity unified space and time into a single entity, space-time, and revealed that mass and energy are two sides of the same coin, expressed in the most famous equation in history, E equals mc squared. General relativity then went further, unifying gravity with this space-time fabric. Gravity was not a mysterious force acting at a distance, as Newton thought, but the curvature of space-time itself by mass and energy. The stage itself became the actor. The second revolution was quantum mechanics. The stable, predictable atoms of the classical world gave way to a fuzzy, probabilistic realm. Niels Bohr, Werner Heisenberg, and Erwin Schrödinger showed us that particles are also waves, that certainty is replaced by probability, and that the act of observation shapes reality. The quantum field theory that emerged was a profound fusion of quantum mechanics and special relativity, describing particles as excited states of underlying fundamental fields. The electron, for instance, is a tiny knot of excitation in the universal electron field. The unity was becoming more abstract, more mathematical, and more powerful. Our modern story is the quest to complete this unification. The twin pillars of 20th century physics, general relativity, which describes the cosmos, and quantum mechanics, which describes the atom, refuse to fit together seamlessly. Where they meet, at the center of a black hole or the first moment of the Big Bang, our mathematics breaks down. This has led to the great frontiers we explored. Particle physics, with its standard model, has unified three of the four fundamental forces: the electromagnetic, the strong, and the weak nuclear forces, and classified all known matter particles. It is a triumph, but it is incomplete. It does not include gravity. Nuclear physics explains the power of stars and the elements they create. Plasma physics explores the fourth state of matter that constitutes most of the visible universe. Geophysics and biophysics apply these universal laws to understand our specific planet and the unique phenomenon of life. And hanging over it all are the great cosmic mysteries of dark matter and dark energy, the silent partners whose nature remains the greatest puzzle in cosmology. So as you drift to sleep, see the whole picture, from Newton's apple to the quantum foam, from Maxwell's waves to the curved cosmos. It is one continuous, connected story. The same laws that govern the spin of an electron govern the spin of a galaxy. We are not just studying disconnected branches of knowledge. We are uncovering a single, deeply interconnected reality. You are part of this reality, a being made of stardust, governed by quantum law, living on a planet shaped by thermodynamics, looking out at a universe expanding by dark energy, and using a brain whose consciousness is the universe's most profound mystery. Rest now, within this beautiful, unified one whole. You are home. Good night.